Standing waves are a fundamental concept in wave physics. They form when two waves of the same frequency and amplitude travel in opposite directions and interfere with each other. Let's visualize this process. We start with two waves that have identical frequency and amplitude, but they're moving in opposite directions along the same medium. Here we see two waves. The red wave travels to the right while the teal wave travels to the left. Both have the same frequency and amplitude. Watch as these waves propagate in opposite directions. When they meet and overlap, they interfere with each other. Now let's see what happens when these two waves interfere. The result is a standing wave pattern. This is a standing wave. Notice how certain points remain stationary while others oscillate with maximum amplitude. The red dots mark the nodes, points where the displacement is always zero due to destructive interference. The green dots mark the antinodes, points of maximum displacement due to constructive interference. Now let's examine standing waves on a string fixed at both ends, which is a common real-world example. Consider a string fixed at both ends. The length of the string determines which standing wave patterns can form. For the fundamental frequency, or first harmonic, the string length equals half a wavelength. This is written as L equals lambda over 2. For higher harmonics, the relationship becomes L equals n times lambda over 2, where n is the harmonic number. For standing waves to form, three key conditions must be met. First, the waves must have the same frequency. Second, they should have similar amplitudes. Third, they must travel in opposite directions. When these conditions are met, the interference creates the characteristic standing wave pattern with stationary nodes and oscillating antinodes. Understanding standing waves is crucial for comprehending many physical phenomena, from musical instruments to electromagnetic resonance. The key insight is that when waves interfere under the right conditions, they create stable patterns that appear to stand still in space. Resonance is one of the most important phenomena in physics and engineering. It occurs when a system is driven at its natural frequency, resulting in dramatically increased amplitude oscillations. To understand resonance, imagine we have a system that can vibrate. When we apply a driving force at exactly the right frequency, the system responds with much larger vibrations than normal. Every object has one or more natural frequencies at which it vibrates freely. These frequencies depend on the object's physical properties, such as length, tension, and mass. A classic example of resonance is the tuning fork demonstration. When one tuning fork vibrates, it can cause another tuning fork of the same frequency to vibrate as well, even without direct contact. Resonance has many important applications. In musical instruments like guitars and violins, resonance is used to amplify sound and create rich tones. However, resonance can also be destructive, such as when wind causes bridges to oscillate at their natural frequency. The natural frequencies of a vibrating string can be calculated using the formula F equals n over 2L times the square root of T over mu, where F is the frequency, n is the harmonic number, L is the length, T is the tension, and mu is the linear mass density. Resonance occurs when systems are driven at their natural frequencies, creating standing waves with large amplitudes. Understanding resonance is crucial for both harnessing its benefits in musical instruments and avoiding its potentially destructive effects in engineering structures.